Okay, we got a new meter to look at. This is the Fluke 115. The reason I wanted to look at this meter is it's a little bit older than these. It's marked 2006 Fluke Corporation. This meter can't do temperature, so of course there's no temperature probe with it. It came with the same test leads that were supplied with the 101 and the 17B+. Not a real big fan of these leads. I mean, they're okay. I would have thought a little nicer coming from Fluke. We can see the 115 is a true RMS meter. This is 6,000 counts. The current cost is $132. Came with batteries installed. And you can see this actually has a bar graph at the base. I had actually used a 115 when I was comparing some of the Flukes against the Bryman that I bought. And one of the things I demonstrated was how well this bar graph worked against the Brymans. You can see it has a DC and AC millivolt range. Update rate on this is 4 Hertz. It even has a backlight. The screen gets a little washed out depending on the angle. It's looking at it compared with the 17B+. The Fluke 107 is also a 6,000 count meter. Of course, you're missing some of the features that are included with this 15, but the cost on the 107 is about $108. Again, very robust meter. When I had the initial 115 here, I didn't run any transient tests on it. This Unity 139C, again, this is also a 6,000 count meter. It has some features that this 115 does not. That would include temperature. And the Unity is about a $47–48 meter. This meter has been damaged, unfortunately, and it's non-repairable. All the rest of these, when they've been damaged, I've been able to repair them. They had sufficient transient protection that actually protected the IC chip. This is the manual. It was supplied with the 115. Nice printed. Several languages. English comes up first. That's essentially your English manual right here. See, July 2006. So we'll go ahead and take this 115 apart. Again, you can see this one's built with the 2 tabs. Very similar to what I see with the AM probes. As I said in a previous video, I like these much better than what's on the 17B+. At least with these I can clip on a power supply and power up this meter to test it. Well, it is pretty tight. You can see how the case comes up through the circuit board on this one. You see they actually have some thread locker on these. TI chipset. Looks like it's Rev 0.019. Lead free. Let's have a look at the switch here. I will say I like some of the clearances on these. Some of the switches are so complex you can just see how they arc over. Some of these more simpler ones, it seems like there's less chance of it happening. Do kind of wonder what RT2 is here. I saw that when I looked at the Unity 139C after I damaged it, that it has 2 different clamps that weren't populated. I do kind of wonder on some of these meters when they design them if they would have gone ahead and populated all the parts. Would it help these meters survive these tests? It's quite the molded piece here. Have to have all that cut out. See some of the grease here. Looks like just the single LED here for the backlight. I guess that's why it's a little bit on the dim side. Some kind of, doesn't look like it's off the plastic. I guess I don't know what that is. See a little bit of it up there as well. It's got kind of a blue tint to it. I don't know what that would have came off of. This is 5KY's Amprobe AM510. It's interesting too on the Amprobe. You can see on a lot of these meters they'll have some kind of a shrink wrap or something over the PTC. Certainly it contains the blast. I have seen these come apart. You know, other than that, I'm not really sure what the purpose of it is. Yeah, it's hard to say what that contamination came from. I was thinking it might have been the circuit board, but it might be like the screw peeled some of this off when it was originally assembled. Just has a little bit of a blue hue to it. On the Fluke 115, they're using a DMM-11AR. And on the Amprobe AM530, it's a DMM-B-11A. I'm not sure what the characteristics are. These both have an interrupt rating of 20 kA, 1000 volts, AC and DC. Both assembled in Mexico. You can see here on this, see, I can't slide that fuse at all. Where the Fluke, on the other hand, you can see, you know, I can just slide this thing fairly easily. You know, it's really not that big of a problem to move it. Looks like the plastic block here is what keeps it from moving over. They probably needed this in here for insulation anyway. Well, it is tight from this mauve up to the body of the fuse. Huh. Yeah. Okay, let's go ahead and we'll try this out against some of the other meters. So on the left is the 107. Again, the cost on that's about $108, and that's a 6,000 count meter. Next to that we have the 17B Plus, and again that's about a $156 meter, and that's 4,000 count. Again, both these meters are not RMS. Next we have the 115, again $132. Next to that the Amprobe AM530, again that costs about $80. And again, next to that is my Bryman BM869S. And again, that meter costs about, I don't know, somewhere $220, $230. Again, all three of these meters are RMS. All three of these will have the bar graph. These two do not. Okay, so this is with 1 millivolt applied. There's something interesting there. So when you go into the millivolt range, the 115 defaults to AC, so you have to select DC mode. Of course, the Bryman remembers everything that you've set it up for last. We could see here the 107, of course, it doesn't have a millivolt range. It's looking with 1 volt applied. And of course, the 17B Plus has to be switched. And so does the 115. I'm assuming, yeah, so if I switch this back to millivolts again, you can see it switched it back to AC mode. So every time you change that back, you have to change this, and the Amprobe works the same way. So you can see now roughly on the 107 we're reading a volt. It's about 2 millivolts out. And this is with 10 volts applied. It'd be interesting to compare these with inside of a temperature chamber and just see how much the temperature affects these. This is with roughly a half volt 60 Hertz signal applied. You can see the Bryman will display the frequency. It's got a split display. This is with roughly a 5 volt signal applied. Again, this is 60 Hertz. This is with a triangle wave applied. This is roughly a half to 9.5 volts. Get an idea how fast these things switch between the ranges and how fast the screen is being updated. I'll set this so the meters don't change through the ranges. So this is roughly a volt. So this is sweeping a sine wave right now. This is every 2 seconds. And this would be every 1 second. This is at 2 times a second. This is at 4 Hertz. This is at 10 Hertz. And again, on the 115, just the first few elements are now being lit. Same thing with the amp probe, but the this Bryman here is basically using that range, the full range. And you can see here, that thing keeps up with this very well. Look at some of the other modes of the 115. Currently it's in resistance mode, and this will be a 10 meg ohm resistor. This is a 1 meg, so 100K, 10K, a 1K, 100 ohm, 50 ohm, a 1 ohm, 0.5 ohm, and here it is with a short. Just looking in diode mode. It's interesting. So again, this is diode mode, and here is with a single diode attached, and with 2 diodes, and with 3 diodes. This is with a 1 nanofarad. This is a 0.1 microfarad. This is a 1 microfarad and a 10 microfarad. I was looking through the manual to see what the maximum DC voltage was, and I noticed under the diode test here, they actually show this thing having the meter beep to show you that it's actually shorted out in diode mode. So if you've got a diode and you don't know that a short is 0 volts, the thing will beep at you apparently. Anyway, so looking at the specs for this thing, this will be on page 7. You can see for both AC and DC voltage, 600 volts is the top end. So I'll go ahead and turn on the power supply and we'll apply a 600 volt signal to it. Again, we'll just use the Bryman for a reference. 603 volts there. It's not too bad. See, both meters are reading roughly the same voltage. Next thing we want to do is a continuity test. Wow. It's a 5 word per minute meter. Yeah, it's pretty slow. So again, the first thing we're going to do is measure our open circuit voltage. Next we're going to look at the short circuit current. Next we'll measure the threshold where it measures a short and an open. Next we'll look at the maximum frequency using a 50% duty cycle. Okay, this is looking at the continuity test results for the Fluke 115. With the 50% waveform applied, it'll run up to 3.1 Hertz where it'll start to skip. This is pretty much on par with the Unity 139C. Again, I'd like something a little faster. This 8 Hertz is pretty much about the bottom end of what I would want. It's able to detect very short pulses though. Again, sub 5 milliseconds. The short circuit threshold is 63 ohms. Very similar to the other meters. But notice the release is 130 ohms. So it's just this huge hysteresis. This is by far the highest hysteresis I've seen. We also look, it's the second highest open circuit voltage, 2.5 volts. The current is also fairly high at almost 300 milliamps. For the next test we'll be running our static discharge, and again we'll be using our piezo grill igniter, and again I'll be running 5 transients, both positive and negative, using each mode of the meter, and then we'll functional test it. If you look at the documentation for this meter, it's printed 2006, and all the meters I've been looking at, like this 17B plus. This was marked 2014. This 101 is marked 2013. I believe when I looked up the 107 it was also 2013. So all three of these meters from Fluke are roughly 8 years older or so than this Fluke 115. And that's part of the reason I wanted to run this meter, is because it is so much older. The only other meter that I tested that was quite a bit older was the Fluke 87V. And that meter definitely is not near as robust as every other Fluke I've looked at. So what I'm wondering is, this being an older style meter, is it going to be less robust? So that's what we're going to answer. I'll just slide this back a little bit so you can watch. Okay. See, it went through a reset. Wow. Well, that's pretty crazy. This meter is definitely a lot more susceptible to it. Huh. You look at how solid some of their other meters are. This doesn't give me a whole lot of confidence. Yeah. Go ahead and test this thing out and see if it still works. This should be roughly 14.5 volts. Oh, you gotta be kidding me. This thing has failed, I think. I can see the 60 hertz. Wow. I doubt that's our transformer. Let's just compare it with another meter here. Yeah, like 14.5 volts. Wow, look at that. That thing is dead. Unbelievable. Alright, let's try some of the other modes here. This will be DC volts. Wow. Again, completely dead. Again, I've just got a precision reference in this box. It's not temperature controlled, but good enough for this. Just look with 5KY's Fluke 107 here. And yeah, it looks fine. So it's not our source. Look at that. What a piece of shit. Unbelievable. Millivolt range. That's dead. Unreal. Resistance. Let's try that. So this will be 10 meg. Gone. Let's try it with a dead short. Look at that. Continuity test. Well, what do you know? Something works. Let's try Diode Check. Does not work. Capacitance mode. Doesn't work. Unreal. Again, that's the one test I'd never expect a meter to fail. Unfreaking real. So I took this 115 apart and I started looking through it, and you know, I couldn't find anything wrong with this thing. Yep, nothing. Really expecting to find some diode somewhere shorted out. Nothing. So I put the board back in here, but we can kind of slide the battery pack in here and have a look at this. So you can see it's in the AC volts mode, and I'm going to go ahead and hook up my transformer. Look at that. I don't have any clue why this thing is back to life. I really have no idea. So here it is in 5-volt mode. Look at that. Dead on. This is in resistance mode, and this is with a 10 mega ohm resistor. Here's with a 50. Continuity test. Read 0 volts. This is in the diode mode. Again, here's a single diode. 2. And this is in capacitance mode. And this is a 0.1 microfarad. No problems at all. And here's a 10 microfarad. Look at that. So I don't know what to even think of this. I'm definitely not real confident in the meter. I can tell you that much right now. The only meters I've seen that had actually failed that ESD testing were the 2 unities. It was the UT61D and the 61E. But why this thing came back to life, I have no clue. That is just bizarre. So I think what we're going to do is put this back together again. And I guess I'm going to call the ESD test sort of a pass, kinda. I don't even know, how do you rank it? It's like it surely didn't work after I was done with it. But it did seem to recover on its own. Does make you want to zap it again, don't it? So let's try it here. Let's see if it recovers on its own. Here's 1, 2, 3. Now can it read AC volts? Let's just see. Yep, no problem. It's still working. Alright. Is it still working? It is. Okay. Okay, here we are in DC mode. No problems at all. Yep. So it's an open. Again, here's a 10 meg. There's a 50 ohm. Continuity test is fine. Let's try the diode test. Again, here's a single diode. Here's 3 diodes. Here's a dead short. And again in capacitance mode. Here's a 0.1. Here's a 1. Here's a 10 mic. Huh. Yeah, so I don't know. it appears to pass the test just fine. It's like it got into some mode that this thing just flat out wouldn't work basically in any mode, and it has recovered. And I basically reran the test, and even with it resetting, I could not get it to repeat. So yeah, I don't know what to make of it, but it seems fine, so I'm going to call it a pass, and we're going to go on with the rest of the testing. For this next set of tests, we'll be using the Transient Generator to create a 220 volt rectified AC signal, and we'll apply this to the meter in all of its modes. So in AC mode, we can see it's putting out 121 volts. DC volts is 237. Okay, the Fluke 115 survives that test, and of course the next step will be running some surge tests through it. So just a quick summary. So far, the Fluke 115, we've passed our piezo grill starter. Of course, it did have a little quirk there. It survived a 600 volt DC being applied to the inputs, and we also applied a 220 volt rectified AC signal. I think the video is probably long enough at this point. Next video we'll continue on with our transient testing, and we'll find out where the 115 fails at. So stay tuned.